Hello and welcome to the last installment of Math 220. This is the last video that you'll have to watch here. We're basically done with the information. There's one more big theorem I have to talk to you guys about, and that's the rank nullity theorem. So I have to define rank. We'll revisit what nullity means, that dimension of the null space, talk about it a little bit in the context of a transformation, and then how this all relates to our big theorem or our unifying theorem. And then we'll be done. That's it. To understand rank and nullity and explain that rank nullity theorem, we need to know what it means to have a row or column space. So basically, we'll be looking at the rows and the columns of a matrix to help us determine a little bit more and kind of come full circle here. So really what we'll be working with here, let's say for some matrix A, the row vectors, I'll use that terminology, the row vectors are just the rows of A. Say this A is n by m. I need some dimensions here for this to make sense. The row space of A is the subspace of Rm spanned by the row vectors of A, the row vectors of A, and is denoted row A. Okay, and that's Rm, which is maybe a little bit misleading, but it's because that there are m entries in any given row of our matrix, right? So if you want to write it out, you can, but it's a little bit weird. Rm is the number of entries in each row. So the span of the rows will be something in Rm, okay? We also have a column space. The column vectors of A are just the columns of A, right? We'll use that to define our column space. The column space of A is the subspace of Rn spanned by the columns of A, and is denoted col A. Okay, so similar definition, but we're working kind of horizontally and vertically in one, and then the other. So column space will be the subspace that's spanned by the columns of A, and row space is the space spanned by the rows of A. Okay? So I want to look at an example here. I've kind of stopped things on this page. I'm going to go to another page and look through an example. Okay, so let's have this matrix A be the following matrix. And I want to reduce this, so I'll write the reduced form here, and then I'll give you a second to copy things down. But just plugging this into a reduction calculator. And I do look at the echelon form here, not the row reduced echelon form. So let's say this matrix reduces to that guy there. You can call it B or something like that. I want to look at the row space and the column space of this matrix. And the first thing you want to do is identify the pivots. Locate the pivots, specifically of B, I guess the second matrix. But we can say of A. Now, the corresponding columns in A to those pivot columns right there, those guys, those will make up a basis for the column space. Okay? So all I need to find are the pivots of A. Those corresponding columns then in my original matrix A, I need just those to span the rest of the columns of my matrix, or span not the entire space, right? I need more to span R3 than just those two vectors, but it spans the space of my columns. It's a little bit weird, but it doesn't necessarily span all of R3. These columns of A corresponding to the pivot columns, the pivots form a basis for the column space, or col A. Okay? So the basis for the column space in this case will be those two vectors, just 1, minus 1, 1, and negative 2, negative 1, 13. Okay? We can also find a basis for the row space. Those pivots are going to help us, but not completely. Right? Basically, what we look for are the non-zero rows now, not the non-zero columns, but the non-zero rows of A to find a basis for the columns, or the row space, I'm sorry. The non-zero rows form a basis for the row space of A. So those two rows then, the first row and the second row in my reduced form, those are going to form a basis for the row space. And I just write those back down. Exactly those rows, but I write them as column vectors just because that's typically how we write a basis. So the basis for the row space will be just those two vectors. And again, I want to remind you of dimension, right? If we find the dimension of the row space or the column space, in this case, the dimension of the row space would be 2. Let me get a color here. Dimension of the row space would be 2 because there's two vectors in that basis, and the dimension of the column space would also be 2. Right? So that's a useful thing to think about. I want you to recall the nullity of a matrix A, because to talk about our rank nullity theorem, I need nullity. It's half of the theorem. Nullity is the dimension of the null space. Dimension of the null space of A. Okay? This new part is what we're going to refer to as rank. The rank of a matrix is the dimension of either the row or column space of the matrix. Okay, so it's how many vectors are in the basis of the row space or the column space. They're the same. Okay, and that's what I outlined on the previous page, is both the row space and the column space had the same dimension. Let's look at another example here. Say I have a matrix A is the following. I got a 3 by 5 for us here. And I'm going to reduce it. Again, give you another second to write the reduced form down. That's my new matrix B. It's in the row reduced form, not just echelon form, but row reduced, because to find the dimension of the null space, it's much easier to look at the row reduced form instead of just the echelon form. Okay. So first thing I'm going to look at is the rank of this matrix. If once I find the pivots, the pivot rows then, or the non-zero rows of my matrix there, those two vectors would form a basis for the row space. So I've just decided to do row space here. I could have easily looked at column space to find the dimension. But right there you can list the rank of the matrix. Once you've reduced it, you can basically read it off. How many non-zero rows do I have? 2. That's the number of the dimension of the row or column space. So the row space of A is those two row vectors. I'll write them down. Those two row vectors. So the rank of A is the dimension of that row space, which is just those two vectors, is 2. Okay. The shortcut is just the number of leading variables or the pivots. That will be exactly the rank of a matrix. It's just the number of pivots. We have 2 pivots, that's the rank. I believe we discussed this before. The nullity is a little bit more difficult to see here. I'm not going to go through exactly the whole process again, but remember the nullity, we find the null space, which is the solution space to the AX equals 0 homogeneous problem. So the nullity is the dimension of the null space of our matrix, which is the dimension. If I kind of expand this, find my free variables here. I have S1, S2, and S3. I have 3 non-pivot columns. If I were to solve that equation equal to 0, that system equal to 0, I would get the following basis, and I'm just going to list them out. 2, 1, 0, 0, 0, negative 9, 0, 3, 1, 0, and 16, 0, minus 5, 0, 1. Okay? If it helps, you might go back and look at the previous video. I go through how to find null space, or maybe the first. I don't remember exactly which video, but it's there. It's there. I find null space for us. We can find it here relatively easy. I'm just glossing over a few details. The dimension of that, there's of course 3 vectors there. So the dimension of the null space is 3. That is the nullity of my matrix. The shortcut here is the number of free variables or non-pivot columns. Okay, so we have some shortcuts. That's really nice. Basically, we need the reduced form. From that, we can discuss the rank and the nullity of our matrix. And those 2 things should always add up to the number of columns in our matrix, right? Basically, I'm adding the number of pivot columns, and the number of non-pivot columns should give me the total number of columns. That's really all our rank nullity theorem says. Okay, so I'm going to write it down for you here. Let A be an n by m matrix. Then the rank of A plus the nullity of A should be m, the number of columns. The number of columns. Okay. In the previous example, we were dealing with a 3 by 5 matrix. Right? So we can determine then basically the nullity or the rank given the rank or the nullity, right? So we can go back and forth. It's very kind of a nice theorem to have. We can always look backwards and forwards and make sure that everything lines up in the place that it should. In the previous example, again, rank was 2, nullity was 3. That's the total number of columns. That should be 5. Right? And this is a useful kind of thing, and I do want to outline that in the next example here. Well, there's my rank nullity theorem. That's one of the bigger things coming from this chapter, and it does correspond, of course, to our unifying theorem. Here's an example. Given A is 5 by 13, there's kind of some random numbers here, and I have a linear transformation defined by that matrix. Okay, if the dimension of the kernel of T, we remember kernel there is basically the same thing as the null space. It's just in the context of a transformation. The dimension of my kernel space or null space is 9. What is the range of T? I want to figure out the range, basically the dimension of the range. Okay, so what I look at here is I want to kind of dissect A and be able to identify what's going on. We think about kernel as, again, the set of solutions to the problem T of x is equal to 0, and in this case, that's A of x equal to 0. And if you remember from the last example, when we were looking at the dimension of the null space, or the nullity, so here we find then the dimension of the kernel, which is basically the nullity, or the dimension of the null space. Dimension of the null space of A, and that's really the nullity. And here that's given, that's a 9. We also then need the rank of our matrix, which is basically going to be the range. Now here first, we need to see that the range is really the span of the columns. The span of the columns, and that's because of the way our transformation works here. I'm taking A, which is 5 by 13, and multiplying it by x. Okay, so when I multiply that out, I need to multiply a 5 by a 13 times a 13 by 1 to get a 5 by 1 out. Okay, so the range of T is the span of the columns of A, or the call space of A. So what we can do then is determine the dimension of that column space, which is the rank of my matrix A, and that's the dimension of our range. That's really what we're looking for. That's what we want from this problem. So I want the rank of my matrix. I know M. I know the number of columns in my matrix, that's 13. And I know the nullity, so I can find the rank. Therefore, by the rank nullity theorem, by the rank nullity theorem, the dimension of the range should be M. Oh, I'll get there, sorry. Rank plus 9 is 13. So really all I need then is 13 minus 9 gives me my rank, or the dimension of my range. The rank of A is 13 minus 9, or 4. So the range, or the dimension of the range, is 4. Okay, so that's a nice little use of our rank nullity theorem, but that's basically how it goes. It's just kind of a three-object equation there. You almost always know the size of your matrix, right? And then try to find either your rank or your nullity and use that to tell you more about whatever the question's asking. Okay. The unifying theorem. 2 new things from this section, and I'll show you our final form, basically, of our unifying theorem. So the 2 things we've added here is that the kernel and the null space have to be the set that is only the 0 vector. If that's the case, then the null space basically has only the trivial solution. All right, the only solution to AX equals 0 is the trivial solution. And that's saying the same thing as number 3, saying the same thing as number 2 there. Once 1 is true, they are all true. So our final unifying theorem from all the information we've covered in the class is the next one here. Sorry, too soon. This is the final version. And I just want to say thank you for a great semester. Thank you, everyone. Sorry that it ended up with just these couple videos here, but I hope you all have a great summer. And I'll get information to you soon about the final. And I should be able to set up a study guide for you as well. So just keep an eye out for those things. Thanks again for watching and putting up with the way that this semester is wrapped up. All right. Take care. If you need anything, you know my email address. Bye-bye.